Okay, we are working our way through the second half of chapter 1 of Journal 3, and that's about pages 60 to the end, to the challenge problems. And so we're into a topic called contour maps. And we had stopped last time, and we're talking about things like this. Right, so we had a couple surfaces here. We said this one had, they're all R3 three-dimensional surfaces. So again, we're in this kind of world, 3 axes. And even though this first one doesn't mention a y, it is still implicitly there, and it's what we called a free variable. And this next one uses all 3, but it was something when we were able to classify them. There's a difference between these two, and you should be able to tell this right by looking at them at this point. This one was linear. It's linear in all the variables. There's like an invisible power of 1, nothing else, no squares, square roots, exponential signs, trigs, nothing that makes this have any non-linearity, so this one was a plane. On the other hand, and so it's again linear things are flat objects, planes in 3-dimensional space, and we talked about hyperplanes in 4 and higher dimensional space. And this one is non-linear. And we ended last time talking about how to graph non-linear things that had at least one free variable. And now we're going to today talk about a slightly more complicated type of nonlinear function. So let's suppose this first one, if we had z equals x squared times y. Now there's no free variables, and it's also nonlinear. Okay, so in that class, when you're nonlinear and there are no free variables, this is your cue that you have to do something beyond the techniques that we've learned at this point. And what we're going to do is something called a contour map. So that's your cue that you need to use a new technique called a contour map. And so that's really the main idea of the last half of chapter 1 is how to graph with contour maps. And this is a little bit more complicated than the types of graph we've done thus far. So they're a bit more extended problems. Okay, the idea of a contour map is that we're going to take this surface. No idea what it looks like just by visual inspection right now, other than saying that it's nonlinear. And we're going to say, well, you know what? There's 3 variables, and so I'm going to have this 3-dimensional space I'm going to draw in, or see it in front of me. But if it was just 2-dimensional, even just temporarily, I'm good at handling 2D. Because remember, our life prior was always back here in 2 dimensions. And so what we're going to do is temporarily treat this 3-dimensional thing as if it were 2-dimensional, and in doing that, we're going to create what's called a contour map. So watch how we do that. We're going to say, again, we're pretty good with x's and y's, so let's just momentarily pretend that this z isn't a variable, it's actually a constant. And we're often going to use the letter k to describe a constant. So we're going to say, suppose z equals k, and we're going to pick a bunch of different values for k, but they're constant values. Right, so I'm going to make a list here of something called z equals k level curves. You'll see this in your journals. You see this phrase quite a bit. And this technique is used on several examples in the journals, and you'll add several more yourself. So to take a level curve, I'm going to pick several different values that I could use for this constant. So let's just pick some numbers. We'll try -2, -1, 0, 1, and 2. It doesn't matter what you pick, but you usually want to pick a range, often some negative, 0, positive. There are some functions for which negative values don't work, right? It wouldn't make any sense on, let's pick maybe another color here, z equals x squared plus y squared. Also nonlinear, also in R3, also needs a contour map, but it wouldn't make sense for the level curves for this function. I'd have to choose things, right? If you square a negative number and a negative number, you still get, squaring those, you get positive. So the only values for z that I could choose here that would make any sense would be positive ones, right? Again, doesn't really matter what you pick. You could have chose -10, -5, 0, 5, 10. You usually want to pick, again, something that covers a range and then to kind of evenly space And you also generally want about 5. There's no rule, no hard and fast rules, but you want usually about 5 before you start to see an idea of what this is going to look like. Okay, so back to our original problem. We're not going to do the blue one, we'll stick with our x squared y. And again, I've chosen these values, and so now I'm going to say, well, instead of z equals x squared y, I'd have minus 2 equals x squared y. Okay, and that has temporarily made the problem seem a little bit easier because there are only 2 variables, x and y. And again, I'm good at graphing those. So I'm going to solve for y like I normally would put it into a calculator or a graphing tool or tech tool. And so this tells us that y is minus 2 over x squared. And I'm going to do this for all of these. So I'm going to go ahead and keep on solving. So minus 1 equals x squared y. I'll just quickly run through these. You can pause the video if you need to check. And we'll just have 0 on the next one. So y equals 0 or x equals 0 solves that. And y equals 1 over x squared. And finally, y equals. We start to see the pattern. And this is what's usually going to happen with these contour maps, is that they create a family of curves in the xy plane. And so a contour map always is drawn in the xy plane. So we'll come over here and draw that. And again, there's some comfort to that because we are familiar with the xy plane. Maybe you recognize these. If you don't, use a tech tool. Go ahead and throw them into Google. Google can graph these. I know what they look like, but maybe just to show you, well, let's just put a couple in, then we'll show you how you can use a tech tool or pull out a calculator and graph these. So this is the minus 2, makes a hyperbola that comes here. And you want to label every time you draw. So this is for the first one, minus 2 x squared. You want to label it with the z value that you used, which was minus 2. Z equals minus 2. And then the minus 1 comes inside. And again, if you weren't sure about those, we'll add the next ones in a moment. I'm just going to get to a screen share here for a moment. Pause this. That's right, Google. Just know that you can graph equations with Google. So it'll show you minus 2 over x squared. That was our first one that we put in. And then if you're like, well, I know they're a family of hyperbolas, but where does it live? The next one, maybe you go ahead and put y equals minus 1. Whoops, minus 1 divided by x squared. And it'll show you in the 2 colors. You can zoom in if you like, pull it down. And you can see the red for the -1. So that was our contour 1 right here at negative, comes inside. Okay, so we get the idea and we see what's going to happen with the remainders. So the z equals 0. This is again called a level curve. Each one of these is called a level curve. The z equals 0 level curve comes in and actually makes these 2 axes. So that was z equals 0, and the y-axis is also a z equals 0. Then we add the final 2 level curves, z equals 1, and z equals 2. Okay. That is our contour map. Our contour map is complete when it's drawn in the xy plane. It has at least 5 level curves. Each one is labeled with a z value that created it. And you might say, well, what is that going to do to help me visualize this surface? Well, this is a key piece. You're going to get really good in the second half of chapter 1 at using a contour map to visualize an R3 surface. And so this was the surface we were focusing on once again, and that is its contour map. And what you do with a contour map is you do what the level curves tell you. So let's take this z equals 2 level curve. It's actually saying, in this instance, this is the z-axis coming out from the whiteboard here. It could be oriented this way, but let's keep it in the orientation here. So the z-axis is this way. And so this is actually saying, this is a level curve at z equals 2. So I'm actually going to pull it up 2 units. The z equals 1 comes out from the board once. The zeros stay. The -1s get pushed through the board. The -2s get pushed through the board. And hopefully that helps you visualize the surface that is created by that. Some of the surfaces that we'll do will be very simple to see. This one's a little bit more advanced one, and we'll come back to that in a bit. As opposed to this one, z equals x squared plus y squared, which is one of the examples in your journals. It's worked through there, and what you would see is that z equals 0. Oops. Makes a level curve that is just a point. A circle with a radius of 0 is a point. The next one, z equals 1, makes a circle with a radius of 1. Circle with a radius of 2, 3, 4, and so on. So that I'm going to draw a little mini picture here for our contour map for this x squared plus y squared. That's the circle with a radius of 0, which happened when I set z to be 0. Circle with a radius of 1. Radius of square root of 2. So this one's got the radius of square root of 2. And so that'd be like 1.4. This would be square root of 3 as the radius. And that was when z was 3. We get a little bit tighter. When z is 4, we get a radius of 2 for the circle. So here was the 2, 1. Again, much better pictures in the journal so you could follow along. But this one is much easier to see what the surface looks like, because now when I follow, the z-axis is coming out from the board, x and y-axes. I keep that one right there, pull this one up 1, 2, 3, 4. Hopefully you see that when you set it in its usual orientation, it creates this bowl shape that is called a circular paraboloid. Again, the journal goes through as you read along. You'll see how it got that name, circular paraboloid, but hopefully you see what it looks like in 3D. You see it in front of you. And this is what the surface looks like drawn in 3D. It's a bowl-shaped circular paraboloid, opening up from the origin, hugging around the z-axis. Okay, we're going to come back to visualizing this one also with a tech tool, because it is a bit more complicated than this one. Let's do one more example on graphing of contour maps. So let's make some space on the board. Pause the video. You don't need to watch me erasing. Okay, we got a clean whiteboard and a new problem. So I want to do one more problem on graphing contour maps in this section. So a typical problem will start like this. Graph the contour map for this R3 function. It's definitely an R3 because there's 2 input variables affecting a third output that makes it in 3-dimensional space. And notice again that there are no free variables. X, Y, and Z are all used and represented. So the technique then is a contour map, but they already gave you the hint. Told you that there. Once we draw the contour map, then we want to use it to visualize and describe what this R3 surface looks like. Okay, so a contour map, again, lives in the XY plane because that's easier for us to deal with and visualize. So if it lives in the XY plane, get a point partial credit by remembering that. So you draw the XY plane, and then we're going to fill that with, using your new vocabulary, something called level curves. So we're going to make 3 to 5 level curves. We're going to pick things like when Z is constant, we'll make a list of some level curves that we're going to try. Again, doesn't matter. I'm just going to try these 5. As I go through the course of it, I might find out that some of these values aren't in the range, and then I may have to try other ones. It looks like, though, I think we'll have no problems with the range of what Z values are allowed. So I think these are going to work. As we proceed, we'll find out. So we're going to temporarily fix the variable Z at the constant value of -2. So we'll say -2 is equal to y minus sine x. I don't really know what that looks like when we manipulate things, move it around, and then maybe it'll look like a familiar function that I can graph. So this says y is -2 plus sine x. Okay, that one I do recognize. Again, maybe you don't, so you use Google or Tech Tool, Wolfram Alpha, or your calculator. Visualize what that thing looks like. So I know sine goes like this. It oscillates here between -1 and 1, and then I shift down 2 units, so I make a sine that starts here. something like that. Every time you draw a level curve, always, always, always label it with the z value that produced it. So this was the z equals -2. And we don't have to really go through the work, maybe we'll just do one more. Plugging in -1 for z, solving for y. We see we're gonna just take that same sign graph and make it start at -1 now. But we know they are a family of level curves, and so they should have this similar shape. Right, always, always, always label it with the z value that produced it. And there's 3 more to do, but we're catching the trend. This was the z equals 0. We put in the z equals 1. More sine oscillating graphs. One more at z equals 2. And that was when z was 2 was the level curves. Now we have 5 level curves in the xy plane, creates a contour map. We got full credit on the first part, graph the contour map for this function. And now we want to use that contour map to describe the surface. Okay, so we now follow the instructions on each level curve. This is a z value, z-axis coming out from the board. So I take the one at z equals 2, I pull that wavy oscillating thing out 2 units, pull this one out 1 unit, leave that one there, push that one through 1 unit, push that one through 2. And hopefully you can see then that this is like back in the usual orientation, if this is the xy plane and this is the z-axis, it's laying back a bit, and it's like this undulating corrugated roof. Maybe you've seen that at Lowe's or Home Depot, that sort of material that's, again, undulated just like the sine waves. And ours, instead of standing vertically, like a vertical sine curtain, it's laying back a bit. So it's tilted at an angle. And so hopefully you see that and you can describe it. You could just write that, again, a tilted corrugated roof or something, roofing material. Whatever verbal description helps you convey to me in the grader for this class, that you understand, that you see what this contour map creates in 3D. Okay, that is our introduction to contour maps, and then a few more videos we'll talk about how we can use tech tools as well that can create these and then help us visualize the 3D surface. That's the main concept from the second half of chapter 1. All right, thank you.